So welcome back. Next is a spotlight talk by Anna Huang. Anna Huang is a composer and computer scientist that holds degrees from Harvard University, MIT, and the University of Southern California. She's currently a research scientist at Google Brain working on the Magenta project. And today she's going to talk about her work on generative models that enable interactive musical experiences for both experts and novices. So Anna, thank you for being with us virtually, and we're looking forward to hearing more about your work.
Thank you for the kind introduction. I'm going to talk about how we can use machine learning to extend the kinds of musical interactions we can have in the composition setting, in the performance setting for novices, and also in some cases musicians. Magenta is an open source research project, and so a lot of the researchers are working on generative models, but thinking a lot about how these tools could be part of enabling different workflows in the creative process. We have a blog where we talk about all our research, and also we have a GitHub with all our models open sourced. Today, I'm going to structure my talk kind of in three parts loosely. First, I'm going to talk about some of our work in generative models, and then how some of them can enable new musical interactions for novices and musicians. And then talk about a little bit about how we want to support a kind of a more musical workflow for musicians. I'll start by one of a work from myself as kind of an intro example. I'll dive a little bit deeper into it to talk about the technical aspects and how we were thinking about interaction when we designed the model. And then I'll open up the space to talk about a range of different models at Magenta. So this was the first work that I did when I joined Magenta when they were starting out. This was summer of 2016. So the problem I wanted to solve is if you're in the middle of composing and you have this partial score, can we build a model that can help you infill these arbitrary gaps and help you glue it together so that you can more quickly prototype your ideas? At the time, the go-to model was RNNs. So RNNs assume this process where you have to go from left to right. And this is because when they're modeling musical sequences, they're breaking it down by these different factors. For example, how are you going to start? And then conditioned on what you've generated so far, what is the next note? And then the next. So this imposes that in generation time, when you use it, you have to kind of use it to generate forward and maybe generate continuations. Definitely, you can go backwards too by modeling the sequence, how it ends, and then how you can lead up to that ending. And that gives you a model that kind of factorizes the joint distribution in a different order. But thinking about music, there's often multiple instruments at the same time. And so we have a grid. So how do we choose an ordering for this grid? We might think, okay, we'll think about the melodies and go melody by melody, and that's an ordering. But that's fairly unnatural because that ordering causes the harmony to be kind of less emphasized. So, okay, maybe we can think about harmony a little bit more. And have the order go through all the notes in a chord and then advance in time. So you see picking and the ordering involves kind of picking musically what you're caring about more. And that's very unnatural because you want something to be general depending on the musical material you have. So we thought, okay, if we want a general model that could support us in in a way, a variety of musical tasks. We want it to be able to do partial score completion, to harmonize a melody, or even to generate from scratch. So why don't we just train it that way by blanking out different parts in the training data and asking the model to do reconstruction? And actually, when we do that kind of training process, the models are learning this. So say in this toy example, you see the first note. By doing reconstruction, the model is learning, given the first note, what is the second note? And this corresponds to a term in a particular ordering. In this case, it happens to be the forward 1, 2, 3 ordering. But at the same time, it also gets, given the first note, what is the third note here, which corresponds to a term in a different ordering. And here you can see, by doing these different blank out schemes and covering all these combinations, then we can get all these components that we need to generate the score, to infill the score in any order. So you can have any context and it would be able to condition on that context and fill in the rest. So for example, here I have 1, 3, 2, and I get the first term from when I blanked out everything, and then so on. And this allows me to have all the terms that I need during test time trained. Okay, so this approach, people call it orderless. It doesn't really mean that we're not modeling the order. It just means we're modeling all permutations of how you might be putting notes onto the score. So this resulted in a model that we named Coconet, because we trained on Bach's chorales counterpoint, and we used a convolutional model. So we actually represent the music a little bit like images. So the music notes as pixels, and then the soprano, alto, tenor, bass as the RGB channels that are input to the model. So here we have an incomplete piano score where some parts are blanked out, and we also have a set of masks to tell the model which parts were blanked out. And then it goes through a model to do the reconstruction, and then we sample from it. So this model is a convolutional a standard network with residual connections. And actually, we don't want to just do this process once to generate the music, because that way we're kind of conditioning on the context and generating all the notes, infilling notes separately. So what we ought to actually do is we do this process multiple times. So first we start with nothing, and then we fill it in. And then we erase some parts and then fill it in again. So initially we erase a lot, but later on we erase less and less, so that we keep the good parts and then start really refining the score. So this is a visualization to show you the process. So initially you see it's very colorful. It's kind of jumping all over the place, and then later on it settles into a harmonization. I'll let us see it again. Yeah, and this plot is showing that this rewriting process actually does improve the quality of the output. The lower is better here. The line you see is if we sampled according to one ordering, auto-regressively, and all these different lines of different configurations of the rewriting process. And you see on the x-axis as the steps you take more steps of rewriting. On the y-axis, you get a better score. So a musician friend of us, we were talking to him about this model, and he said like, oh, can I compose a melody just for your model? So I was very honored, but I waited for many weeks, and this is what he sent to me. Initially, I thought it was a joke, but later on, when I heard the very end, I knew it was a trick question, that this tweak can be really hard for a model to anticipate if it was generating from left to right. But because Coconet is able to do this rewriting process, it's kind of rewriting the music in all directions. So this is what the model came up with. And this is the same interaction that you have for the doodle. So last March, we launched this kind of little toy composing experience where.
How does it handle classic riffs? Let's find out. Let's start with, you recognize this. So I can change the key with this button. The key is E minor, so that's G major. All right, let's start with an E. E to G. Back to E, to D, C, and B. This sounds great. Now let's click the harmonize button. It doesn't sound too bad, right? It sounds pretty awesome. So I actually read that we're meant to listen to it, and if we don't like the results, we can just retry and retry till we find something that works for us. But I think this one is pretty cool. But now, how does it sound if we play these 4 voices on a guitar? On 4 guitars. Let's find out.
So in 2 days, a lot of people around the world tried it out, and the model harmonized 55 million of these melodies, and people spent 350 years of time composing with it. So this really showed just a little bit of interaction could go a long way, but definitely there's a long way to go in terms of really enabling a more natural and musical interaction. So later on in my talk, I'm going to talk about some models that really push this forward. So the 3 sections that follow is on the models, the interactions, and the workflows. I'm going to talk about the models first. The 3 models I'm going to talk about is Music Transformer, that really tries to extend the kind of the scope and the realism of music that we're able to model. So not only the notes and the back chorale case, but also onto the aspects of performance, the expressiveness, and the interpretation, and also trying to get a longer term structure. So you start feeling that there's some story and intention going on. This is a visualization to show how much the performance varies the original score. The bottom, the colors are showing the dynamics that the pianist is interpreting the score with, and also how the expressive timing is being shifted. So prior work, Performance RNN, they came up with this event-based representation that allows us to capture those nuances. For example, it doesn't just capture the notes that are played, but also the velocity. And also it has a very flexible kind of advanced clock event that allows us to capture a very expressive timing. So this is a visualization of a piano roll, and also the self-attention that a transformer is rendering as it's generating the music. So this is how it's looking back into its memory and into the context to see the self-references. And the gray parts I manually highlighted, you see the themes recurring and coming back. and how the self-attention is looking back at those sections. So next, I'll play you a visualization of the piece being played and the self-attention accompanying, being visualized on the fly. Next up, you'll hear a colleague of ours, Pablo Castro, jamming with Music Transformer. So he's in that case, the disc clavier piano was playing the Music Transformer part, and Pablo was jamming on top of that. So now, wave to MIDI to wave is an approach where we wanted to really extend into the audio domain. And the nice thing about being able to analyze and synthesize audio is that we can do transcription, where we can transcribe the performance nuances of the performer, because a lot of times MIDI is synthesized in a more kind of based on score. But here you can get MIDI that's actually transcribed from the audio. And then that gives us symbolic data to train a music transformer. And then in this case, we use a wavenet to synthesize the sound. So the next sample that you'll hear is a music transformer trained on transcribed piano music and synthesized with wavenet. The third model I'm going to talk about is DDSP, which stands for Differentiable Digital Signal Processing. And the idea is, before we had wavenet to generate the audio, which goes sample by sample, and it's a very large model to kind of model that low-level structure. DDSP is an approach where we have a lot of knowledge about how sound and instrumental sounds are synthesized. Can we use that as part of our model to make our models much more lightweight and much more interactive? So it uses, it trains a neural network to actually learn the parameters to control, for example, an additive synthesizer and also a filter noise synthesizer, and then goes through a reverb module. And the really cool thing about it is the model is actually taking from the user's audio the pitch and also the loudness information, and then using that to control the signal processing units. And you can imagine training these models on different instruments and just taking the pitch and loudness from another instrument performance, and then that allows you to do tone transfer. So for example, Hanoi. in this case, DDSP tone transferred Hanoi singing into the saxophone, and you hear all the expressiveness that Hanoi in some ways is trying to imitate the saxophone, the different expressive aspects, and that got transferred actually onto a saxophone. And next we see another example by a musician, Andrew Huang, and this is how he used DDSP.
Experiment, I want to try and use the system completely wrong, like feed it some audio material that it's not really meant to digest. All right, so we got a fun modular patch. I ran it through all the models, and my favorite results were with the tenor saxophone. Now, what if we layered that on top of the original sound? Oh my God.
So next I'll talk about two more models and that enables different kinds of interactions for novices. Music VAE is a variational autoencoder that allows us to embed discrete melodies and also in some cases multiple instruments into a continuous space. So then you can do really fun things with interpolation. So for example, you can do that with sketches also. So here you see a cat being more interpolated into a piglet, and also a melody, two melodies being interpolated. So Catherine took this model and created latent loops where you can put 4 different loops in different corners, and then it gives you a palette of interpolations that you can explore. And she actually even took this into an installation, and this is the experience that she built for Sonar. Next up is Piano Genie. So Chris came up with this really clever way of mapping the 88 keys on the piano onto 8 latent buckets. That way you can actually play the latent buttons to produce a piano performance. This is him performing his instrument. And this was also used in a live concert setting. So these balloons, these balls that you see are corresponding to the keys that Chris was playing earlier. And then later on, you see how this is being kind of augmented into a concert experience. So switching gears, we're going to talk about workflow. And recently, there was the AI song contest, and we took this opportunity to do a kind of in the wild study to try to understand how musicians and developers use AI in the songwriting process. And what we found is, instead of using one giant model that's very expressive, they used many smaller models that corresponded to the musical components that they wanted to control. For example, they would have a chord model to generate chord progressions, and then conditioned on that, they would generate melodies and bass lines. In a way, they were kind of routing these models in different ways. And there's kind of this nice connection or metaphor to kind of these guitar pedals that musicians use to create different effects and route them into kind of a more kind of personal sound. But at the same time, this imposes a lot of challenges, because these smaller models and the musicians really have to juggle a dual process of kind of debugging the musical ideas, and also debugging how these models work and fit, and trying to steer them into kind of the musical context that they're trying to work in. So Magenta Studio is this idea and a series of plugins where different models are different plugins, and you have it in the Ableton Live environment where musicians are composing. So at the same time, while you're exploring your musical ideas, you can also explore these plugins and see how their material might help augment and create some of the variation for you. In this case, we're showing a demo by John. He created this Drumify interaction where you can give it a line, and then it would generate the drums. So in this talk, I talked about some models and how it can enable interactions and some ways to better support using machine learning in a musician's workflow. A bonus track, if you want to take a minute to kind of chill during this conference, check out Verbert's Lo-Fi player, where you can interact with a room of music, kind of bringing in instruments and out, and also even doing some interpolation from a music VAE model to generate the melodies for your room. Thank you, everyone. All our projects are on our blog. Please check it out, and thank you for listening.
Thank you, Anna, for this wonderful presentation. There aren't currently any questions on Slack, but I have a few questions. So I was really curious. I really liked the beats to saxophone conversion. I thought it was really interesting. And I was wondering if you're aware of other artists using these tools in subversive and sort of non-conventional ways. So, for example, when you were talking about the score completion project, I was thinking, wouldn't it be cool if the system generated the least possible continuation for what I have written, you know, as a way to help you get inspired, maybe get out of a creative block. So I was wondering if you're aware of such approaches.
Yeah, definitely. I think a lot of times using these tools, like the part of breaking it is the creative and fun aspect, creating something very unexpected. For example, with a lot of these models, you can play with the temperature, and it can kind of control how adventurous it is. In particular for DDSP, yes, a lot of musicians are starting to use it, especially because there's tone transfer as a user interface that just allows you to kind of record your sound and upload sound clips. So for example, musicians have been using it to kind of create portamento on instruments that don't naturally kind of have that kind of pitch glide ability, and really kind of mixing and matching different ways to augment our existing palette.
Meanwhile, people have typed in some questions. One of them is, are there any plans to improve Magenta Studio to include the transformer architecture or DDSP?
Yes, so DDSP is definitely on the way. For transformer, it's, part of it is kind of the serving infrastructure. A lot of the models in Magenta Studio is in JavaScript. So that's kind of a process that we go through to try to get the models out. And hopefully, yeah, as we speed up these models more, speed up the transformer models in JavaScript, then we'll be able to incorporate them.
Great. Next question. Do you survey what musicians and composers might find useful in advance, or distribute models once they're done and just monitor what happens?
Yeah, we have a kind of a loosely coupled participatory process. So we have our GitHub is open source, so the community can use it and give us feedback. We've also had kind of user study groups with, for example, Cal Arts. We went down to LA to work with the students and brainstorm. And also the AI song contest was also a great opportunity for us to kind of understand what are the current needs and challenges. And hopefully we can kind of create this feedback loop of incorporating a lot of those into our research.
Great. And I think there is one last question on Slack. What are some ideas you have that you want to do further research on?
Yeah, that's a really great question. I think being able to come up with a more control. These control could be like allowing users to define kind of higher level controls that we can try to help learn on the fly. And maybe some of it is the leveraging the latent spaces and being able to kind of very quickly identify kind of the vectors and directions that can take us in interesting directions. And kind of really combining that with like the sound and DDSP. And
so yeah, we have a lot more questions actually. So let me see, I don't know if we have time for all of them. So the next question is, these are various and impressive systems, but they are mostly very specialized in terms of input, output, usage, etc. How do you see the issue of designing more generic systems?
Yeah, that's a really good question. I think DDSP is kind of a step towards that direction where you can really take sound and extract different features from sound and be able to do additional processing on top of it.
Yeah, I mean, there are a lot more questions. I'm not sure if we have any time left, but you can always ask your questions on Slack and Anna can answer later. So we can move on to the next Spotlight presentation. So once again, Anna, thank you so much for this very interesting presentation. And thank you all for your questions.
Thank you, everyone.